Is this energy recovered back? If so, when? So I can show you if I take, so this is the inductor solenoid, right? So what did we say about the magnetic field? So as I flow the current, there is going to be some magnetic field around this. Okay, so let's say this is north and this is south, something like this. So as I start flowing, say 0 amps, 0.1, 0.2, the magnetic field is slowly increasing, right? So when it is 5 amps, it is stabilized. The magnetic field is also stabilized. But once I switch it off, right, the current is slowly coming down. From 5 amps, it's coming down to say 4.5, 4 amps, 3.5, 3. So it just keeps on dropping, which means the magnetic field will also collapse. It will slowly come down, which means this magnetic field energy, as it collapses, this will be converted into electrical energy. Okay, that is what is your induced EMF. So to your answer this question, is this energy recovered back? So do you folks remember the LED was glowing when I break the circuit, right? Why would it glow when you are breaking the circuit? So when you break the circuit, this magnetic field is collapsing, which means the magnetic field is getting converted to electrical energy. Okay, that's what you are supposed to write. Is to answer this in between question, is this energy recovered back? Is this energy recovered back? The current is switched off. The magnetic field energy, magnetic field collapses. Collapses means it slowly reduces. Collapses, magnetic field collapses, and the energy is recovered back as induced EMF. So that's the reason we saw the LED was glowing when you break the circuit. Then it says derive an expression for the energy stored in the coil inductor in terms of L. So this derivation is very simple. So look at this. You know that again, as I said, the starting point is very important. So W is equal to work done by charge coulomb is your voltage. What is this? Work by charge is voltage, right? So that means we say this is EMF E. So if I say the same thing can be written as dW by dQ is equal to E in terms of calculus language, differential calculus. Maybe again let me rewrite it. So W by Q is equal to E, dW by dQ is equal to E. But just now from your mutual induction, right? So do you folks remember this? N d phi by dt. So this one we said. So this is equal to L. This is what we did in our self-induction derivation. So let me not rewrite this. So if I want E, what can I do? L into di by dt. So in place of E, I am going to put L into di by dt. dW by dQ. So L is a constant. So the clue here is they asked you to find the energy stored in the inductor. Energy and work are linked, right? Energy and work are almost the same. So that means that's why we are starting from work here. So work and E are related by work by charge is your voltage. Voltage is nothing but EMF. Okay. So you should know that your derivation is asking for energy. So energy is linked with work. So that's why you are coming to this point. Okay. If you study it like this, it's easy for you to remember. Otherwise, you'll be blinking where to start. So now I want energy, which means dW. So please listen carefully. So dQ comes on this side. So di by dt, dQ. What is dQ by dt? Current, right? Change in charge divided by change in time, right? So dQ by dt can be written as I. So that means Li di. I'm hoping that by this time in your maths, probably you have already reached applications of differentiation, right? So this is one such thing. You have to convert things in such a way that it can be integrated easily like this. Okay. So maybe the integration is coming a little bit later. Any of you have started integration already? You started? Okay. Finished? Okay. So look at this. So I told you work is related to energy, but this is only a small amount of work, right? So if I want the total work, what should I do? I should integrate it, right? So I'm sure, even if you don't know what is integration, we have been using this. So I have to integrate it on both sides. So integration means for a small change in work, this is the value. So if I want the total energy, right, I should integrate it on both sides. So it means integral of dW, integral of Li di. So this becomes W. L is a constant. So integral of x dx is h squared by 2, right? So yeah, I squared. So I'm glad that Javin is awake today, right? So if you don't know what is integration, it's the reverse of differentiation. So if I differentiate this, what will happen? 2 will come here, 2 minus 1 will become 1. So it will be 2 cancel, so I will be getting I. Okay, so it's here we are doing integration, and what I am saying is if I differentiate this, I will get this back. Okay, so differentiation and integration are opposite. So that means energy is, so sometimes instead of W, right, we use the letter U. So I can write it as U as energy. So energy stored in inductor. U is equal to half Li squared. Okay, so after this, I told you work and energy are almost the same. So instead of writing it as W, we write it as U, which is use your energy.